Hello again. Now, in the last problem, we proved this interesting result that the centroid of a triangle cuts the medians in a 2-to-1 ratio. So, what we proved in the last problem is the fact that all these ratios, AG over GD, BG over GE, CG over GF, they're all equal to 2-to-1. The larger side of the median is twice as much as the smaller side. Now, how can we actually use this to our advantage? So, problem 7.18. Triangle PQR is an equilateral triangle with a side length of 12. Find the length of the inradius of triangle PQR. So, let's make our equilateral triangle. So, we actually have a nice tool here. Angle with a given size. Now you create one point and make another. Say you want your angle to be 60 degrees. And what do you know? It actually gives you some points that you can work with to make a perfect equilateral triangle immediately. Because, of course, all the angles must add up to 60 degrees. So we have an equilateral triangle. And I know that the side lengths are 12. Now, find the length of the inradius of PQR. Well, inradius, if we remember, is the circle formed by the tangent lines of the triangle. So, in order to find the inradius, we need an incircle. And to find the incircle, we need an angle bisector. So on GeoGebra, we have our angle bisector tool. So I'm going to select my 3 angle bisectors here, here, and here. That way, now I have my inradius, which I can then label as I for inradius. I mean, not inradius, in center. Now I can form the incircle. So circle with a center tool, center at I, and we get just about at those points there. So we get this following diagram. Now, if I wanted to clean it up a little bit, what we can do is draw the segments from these points, and that way hopefully this works. We can just erase each out of the greater lines, so we're left with just the lines we really want to pay attention to. So that is one of the radii of a circle, IK. We can create another radii, IL, and one more radii, IM. Now, since this is an equilateral triangle, and we use the angle bisectors to create the incircle, that means that this angle here must be 30 degrees. And since we know the angle bisector is going to hit at a 90-degree angle, since it's an equilateral triangle, then I know that this angle is 60 degrees too. That looks like a 30, 60, 90 triangle. So, now I'm trying to find the length of the inradius of PQR. I mislabeled all that, but whatever. So, alright, the inradius, alright, just pretend, alright, whatever. We're just trying to find the inradius. So, I want to find out what KI or IM or IL is. Well, I have this 30, 60, 90 triangle, and it has a hypotenuse. Here, I'll highlight it so we all know which one I'm talking about. We have, this is our 30, 60, 90 triangle. Now even shade it in a nice blue. Now it has a hypotenuse of 12. So let's take our pen, and if the hypotenuse is 12, the side opposite to the 30-degree angle is half as much, so that must be 6. Which also means that the height, or the side opposite to the 60-degree angle, is whatever 6 times the square root of 3 is. So I know that IL is 6 times the square root of 3. Well, that gives me the entire distance from I to L, but I just want... oh, that's so confusing. Alright. This is L. L right here, and the center is I. Okay? Ooh, okay. Well, actually that looks ugly too. I can just change this to capital L. There we go. So, well, alright, I'm confusing myself a lot right now. Alright, this is just going to be M. Whatever. No. Oh my gosh. A. Okay. So that means that this is an IL. Sorry for all the confusion. That would be AL. AL is 6 root 3. 30, 60, 90 triangle. Alright. Now I'm just trying to find IL. I do not need this entire line. But I should notice what's interesting is that this angle bisector cuts this side in half. 6 and 6. Because it's an equilateral triangle. And what's really interesting is that we just learned about medians. How that is the line from the vertex to the midpoint of the opposite side. So actually AL is a median as well as an angle bisector. This doesn't typically happen, but it did happen in this case. And what did we just learn about angle bisectors? Well, we learned that, not angle bisectors, medians, that the larger side is twice as long as the smaller side. So that means that AI over IL is equal to 2 over 1. Well, if that is true, and we imagine, take over here for a second. I'm just going to draw, I know it's funky and out of the way, but let's just pretend that this is the same thing as in a triangle. That's our median. I know this has a 2-to-1 ratio, which means that AL, the entire segment, if this is a 2 and that's a 1, that would be, AL would have to be 3. Which means that if I were to come up with a ratio of the entire line AL to the part I want IL, that would actually become a 3-to-1 ratio. So AL over IL is equal to 3/1. Again, because if AI and IL have a 2-to-1 ratio, then the side that contains all of them has to kind of be imagined as your 3. And if you compare that with the smallest side 1, it's a 3-to-1 ratio. Now, we know what AL is, so I can start substituting some stuff in. AL is 6√3. And we have that over IL. And that's equal to 3/1. Or just really 3. Now if I multiply IL on both sides, I get that 6√3 is equal to 3 times IL. Dividing by 3 on both sides will finally get me that IL is equivalent to 6 divided by 3 is just 2. 2 times the square root of 3. And that is our answer. So, we had to use a lot of information, 30, 60, 90 triangles, in circle, medians, but once we apply all that information to the problem, it doesn't end up being so bad.